Testing, testing, testing. I don't think I have audio right now for some reason. Hmm. Okay, I've confirmed I have audio. Okay. So I think let's try. I guess I can wait a little bit longer for people to show up, or I can just start the presentation now. Okay. I think I'm going to start the presentation now. All right. Okay, that worked. Great. So this is the second Ignite Robotics software training. Specifically today, we're going to be talking about controlling hardware, specifically for teleop and autonomous, and do's and don'ts regarding that. Okay, so hello, my name is PJ Weatherall. I'm a senior at the Colorado School of Mines and a software mentor for the Clueless. Yeah, that's all you need to know about me, really. So, as I mentioned a little bit earlier, specifically what we're going to discuss is we're going to discuss creating and initializing hardware, controlling motors, controlling servos, teleop do's and don'ts, autonomous do's and don'ts, and localization and navigation in auto. So we'll start with creating and initializing hardware. All right. All right. So let's begin by creating the variables up here so that they're globally accessible within this class. So we need to create a motor. So we'll call it a DC motor. Alt enter to import it. We'll name it motor just because. And then let's go into here, the init. So all of your code that initializes motors and stuff should be run in init. And that's basically when you click the start button, it puts you into the init. And then after you click play, it puts you into the loop. So the init just is where you do your one-time declaration stuff initialization. So in order to create a motor, we have to do motor equals hardware map dot get DC motor dot class, and then the name of the motor inside of the configuration. So when you go to configure your robot or whatever, you put a specific name for the motor, and that's what you put in here. So I guess we'll just assume you named it test. I don't know what the name would be for you guys specifically, but just make sure you change that. All right, and now let's talk about setting the mode. So there's actually a few things you can do with the motor. So for instance, you see there's all these enumerations here. So we can do set mode. And there's four main modes we have. We have run to position, run using encoder, run without encoder, and stop and reset encoder. So I'll just give a brief overview of all of those really quickly. So run to position basically makes the motor go to a specific tick count. So if you say go to 100 ticks, it'll just automatically go to 100 ticks. There's some problems with this. It's slower than if you did a manual PID, and also it is sometimes difficult to get it working properly, so most teams don't use it. Additionally, there's run using encoder. This just basically changes it from a set power on the motor to a set velocity, so it gives you a percentage of the maximum velocity. This also is not used very frequently, and the main reason that this one's not used is because it caps your max speed at like 80% or something, which is kind of a problem if you want your motors to be really fast and do all this stuff. Okay. Then let's go to, we'll do stop and reset encoder. So your encoders have something called a tick, which is ticks, which is their position. Stop and reset encoder just zeroes that out. So if they're at 100 and you do stop and reset encoder, then it'll go to 0 ticks from that position onward. So it's just a reset. After you do a stop and reset encoder, you then have to set the mode again because it's in mode stop now. So the main mode people use is run without encoder. And this is just your standard motor. You apply a power, and that's a percentage of the maximum power that the motor can receive. Okay. Now we'll go into using motors. So down here in the loop, we can do motor dot set power. And this just tells us what power we apply to the motor. So I'm going to take the gamepad input, so gamepad1 dot, and we'll do left stick Y. And this means as you move the joystick on your left stick from gamepad 1, it will update the power that's sent to the motor. The range of powers you're allowed to send are -1 to 1. So obviously -1 will be backwards and 1 will be forward and 0 will be stopped. Yeah. Now we can also get the position. So we'll do an int called pose, and it's motor dot get current position. Again, this returns the tick value. So these aren't in like any useful units. These are just kind of, well, they're in ticks. And you have to convert those out into like real world units if you want to use them. Okay. And then, yeah, that's all I think I need to show for that. And now we'll talk about servos. So there's two types of servos. There's continuous rotation, and then there's servos. A servo means it goes to a specific position inside of its range. So you'll set it and it'll go to a specific angle. And continuous rotation servos are basically just like miniature motors with significantly less power. Yeah, they're useful because obviously you only have 8 motors on your robot, and sometimes you want like a smaller packaging, but you want it to be able to rotate. Like if you look back at Freight Frenzy, a lot of teams spun the carousel using continuous rotation servos because you didn't need a motor for something that small. Okay. And it's a similar idea for declaring it. We do hardware map.get and then servo.class and then the name that you put in. So we can call this, I don't know, test again, because why not? Or test servo. Doesn't really matter. It's whatever you put in the configuration as we discussed earlier. So now servos specifically have a range of 0 to 1 that you can use. So there's 0 to 1 for servos. And 0 will be one end of its range and 1 will be the other end of its range. It's kind of hard to tell where exactly those are unless you use something like a servo programmer in order to force it to go to a specific end. And that kind of brings me to the point of how servos tell their position and what you can get from a servo. So servos internally have a way of telling their position, but they don't give you access to this wire. So unless you buy a specific servo that has access to that wire, when you set a servo's position, you have no clue when it got there or if it gets there at all. Like if something gets in the way, you can't tell. You just send these PWM waves to it, which is pulse width modulation, which is just the distance between the peaks of your wave. Um, and then, yeah, it just moves there. It doesn't. You have no control or no way of seeing if it's gotten there or not. So we just do servo dot set position, and then we can do gamepad 1 dot right stick y, and then because this is between 0 and 1, we're going to add 1 and then divide by 2 in order to get the ranges to line up properly for the stick. Okay, I think that we have gone over everything there, so we'll go back to the presentation now. Great. So another thing we're going to talk about is not using sleeps and while loops in your teleop code. And there's just a pretty simple reason for that. But first we have to go over what is a sleep. So a sleep is just an interrupt or delay in the code. It stops everything else from occurring while it's waiting for this to elapse. You can see specifically it has its input in milliseconds. So milliseconds are thousandths of a second. So 1,000 milliseconds is equivalent to 1 second. In this particular case, it is just sleeping for 1/10 of a second. And then while loops just repeat until the condition is false. So in this case, once some condition is false, it will stop and we will exit the loop. So if we think about a main control loop, right, where everything's happening and you update things in the loop sequentially, if you put a sleep or a while loop, it can add an arbitrary delay in your code. So when you try to update something, it'll take significantly longer to update because the program's busy doing something else instead of reading your inputs. This is not ideal for having code that works well. There's actually quite a few problems where like you can press forward and then you click a button and then you just drive into a wall because your robot never updates the values that it sets to the motors because it's trying to do something else at the same time. So if we go back to the code for a second, if I were to insert a sleep here, it's not like sleep. Okay, whatever. I'll do a while loop. We'll say like int I equals 0 while I is less than some very big number, I plus plus. And basically we've just added a massive delay in the code here. So if we were to set the motor power to 1, right, so it's like going forward, this here will take up a ton of time. So it'll take a really long time before we get back up to this front bit over here to reset the power again for a different value. So let's go back to the presentation. So an example that we were kind of talking about earlier, but this is a more concrete example, is let's say you have a while loop that waits until your slides are busy and you have a button that starts the slides moving up. Say you wanted to deposit this here and you need to move the slides upward. So when the driver pushes this button to lift the slides up and it goes into this while loop, it locks you out from doing everything else. All the other update stuff is no longer available to you. And that can cause, a lot of issues. Specifically, if you're trying to control another mechanism at the same time, like the drivetrain, for example, you can end up just having no control over anything. The main reason things like this are taught is because it's very safe. As I mentioned, you're only controlling one thing at a time. As long as you avoid controlling multiple things at a time, you'll never have any real problems. And you're unlikely to break the robot because of that, right? Do one thing at a time. But there are some issues. Specifically, only doing one thing at a time does mean that you have problems where your code is slow because you're not able to parallelize anything. Like you can't lift your slides while doing anything else, which can cause issues with, if you're trying to lift your slides and drive somewhere, can't do that. Makes you slower because you're waiting for your slides to go up and then you have to drive somewhere. And that in itself causes difficulties in driving because if you have to sit there and wait, it makes it harder for you to understand what you're doing. And then in general, this is not a unsolved problem. There are ways of doing this that are more efficient and don't cause these issues. All right. So here's a basic overview of some solution that would be better. So we begin by checking if the driver inputted anything. Then we update the target robot position, and then we update all the hardware. So instead of using individual while loops to control each thing, we just use the main while loop as a loop, and we have if statements to check if stuff has happened. Specifically, when we do stuff like this with like pressing buttons and stuff, we need to know something called a rising and falling edge inputs. So when you press a button, oftentimes you want something to happen the moment you press that button and not after you let go, etc. So we're going to go in and show how that works. Okay. So if you think about, here, I'll just delete this code because we don't need it. So if you think about how like a button works, every time that button is pressed, it's returning that it's pressed. So if we have something like if gamepad 1.a, so the A button's pressed on gamepad 1, this will trigger for every time the gamepad is pressed. That can cause problems, specifically like let's say you wanted to add 10 inches to your target height. So let's create a variable, global variable called int target equals 0. And whenever you press this, target plus equals 10. If you hold down this button, for every loop, it updates by 10. So the values will grow extremely quickly. It'll be like impossible to control. So instead, we just want it when we first press the button or when we release the button, we want it to make an update. So what we can do is we can create a Boolean for the last value. And we'll set it to false. And then we can create a Boolean here for the current gamepad A value and set it to the gamepad 1.a value. And then we can say if the gamepad A and not last gamepad A, then we do something. So this is basically saying if it's the first time the button is pressed, i.e. the button's pressed and last loop it wasn't pressed. And the final thing to finish this off is to set last gamepad A equal to gamepad A. And there we go. can do the same thing here, and this time it only updates the first time you press the button. There's other stuff you can do, like if your gamepads have some really bad debounce, i.e. when you press a button, it registers multiple presses and unpresses. There's some ways to get around that, but that's out of the scope for this lesson for right now. Okay, great. Let's go back to the presentation. All right. So let's talk about the robot you guys have. So this general drivetrain is what is in the kit. Basically, you have two motors connected to Omni wheels and then some free-floating wheels in the front. This is pretty great because it allows you to make turns with, with the back of the robot. It's pretty nice. Allows you to turn on the spot. It's a very simple drivetrain, just a simple tank. So in order to get it to move properly, though, we don't want to just rely on like setting powers and then waiting. So let's talk a little bit about getting it to drive a specific location. So motor encoders, as we talked about a little bit earlier, use small readings called ticks to measure how much the motor has moved. And then we can use these to calculate a ticks to centimeters and then drive a specific distance forward in centimeters based off of that. The circumference of the wheel is the distance the wheel travels when you rotate a full rotation. So if we know that, then we can calculate the amount that the robot moves per tick using the fact that there are so many ticks per revolution. All right, so let's show how to do that in the Android Studio. Okay. I'm going to a new class over here called Drive. The main thing that's already been set up here is I have the wheel diameter and the ticks per revolution of a motor. And then also I just set up the motors so we can get started on just programming the actual movement. So we'll do public void drive distance, and we'll pass in a distance. Okay. And then, as mentioned in the slides, we can calculate a target ticks, or we can convert the current distance or current ticks into a distance. So we'll do the way that's mentioned in the slide. So double target ticks is the distance times ticks. Oop, wait, first we have to do something else. We have to find the ticks per centimeter. And that is going to be equal to our ticks per revolution divided by our wheel diameter. So very simple. So then we'll do, wait, is this, should be like 2 pi wheel diameter. I'm sure this is fine. I have not thought about this enough. We'll just assume this is all good. So then we'll do times ticks per centimeter. Okay, so that's the target ticks we want to drive, and then we'll reset both our right and left motors. So right.set mode, and we'll reset, so set mode, DC motor, stop and reset encoder. Set this to left, and then we'll do the same thing, but setting it back to run without encoder. And now we can get the pix traveled. So we can do double pix traveled, and we'll just set that to the right dot get current position plus the left dot get current position divided by 2.0, because that's the average of the two that have moved. So then our error is equal to our target ticks minus our ticks traveled. And while our error is larger than some number, so the magnitude of the error is larger than some number, is greater than, we'll just say like 200, we will do movement. So we'll just copy this back in to make sure that the error updates. We can set these equal to 0 at the start. And then we can simply do right dot set power to the error times some constant. So in this case, I'll do 1 over 20 times ticks per centimeter. So basically this is saying that the stopping distance will be 20 centimeters. So we'll start slowing down at 20 centimeters away from our target. And we'll do the same thing for the left. More time just looking up here at the ticks per centimeter. So it's ticks per revolution, and then per 1 revolution, it should be pi times the wheel diameter, if I'm not mistaken. Second, yeah, ticks per revolution, and per 1 revolution you have pi d. Yeah, I think that's correct. Okay. Anyway, let's go back to the presentation for a second. So we can do a similar thing for turning now. So we can use the IMU. So inside of your control hub, there's just a angle measuring device. It actually measures rotational velocity, but we can use it to get the angle. And so we can basically set the angle that we want the robot to turn to, and then go to this. So specifically, we create a way of turning the robot to get a target heading. We find the error. This is the amount the robot needs to turn, and the direction. And the direction is signified by the power, or sorry, signified by the sign, whether it's positive or negative. And the amount of power we need is signified by the size of the magnitude of the number. So then we get target heading minus current heading. It is that value that we need to calculate. Okay. So what we can do here is, if we want to have it turn degrees, we can begin by taking in a target, which is the number of degrees we want to rotate to. Then we can simply reset our IMU, so IMU.reset yaw. So in this particular case, yaw is the heading of the robot. And so we're setting it to 0. Then we can do double error is equal to the target while the magnitude of our error is greater than like 10 degrees. So while we're off by more than 10 degrees, we can find error equals target minus IMU dot get roll pitch yaw angles dot get yaw, and then we have to input the degree angle unit, and then that gives us our error, and then we can just simply set our powers. So right dot set power error divided by 90. So basically at 90 degrees we'll start slowing down, and then left dot set power error divided by negative 90. And the reason we have a negative down here is simply so that the robot spins. If both were positive, the robot would go forward. We need one to go backward in order to cause the robot to spin. All right. And then at the end, we'll just set the power to 0 for both of the motors. Oh wait, shoot. I did not do any. Oh no. Well, that's a problem. Should I just restart this all? Well, I guess we can write the class again if you guys want to. Sorry. Okay, let's just rewrite this all. Well, I'll do a run through. Okay, so again, we have our function here, and we pass in the parameter of the target. We do a reset on the IMU yaw. This is a very simple way of doing it. There are more complex ways that will be more accurate and don't accumulate as much error, but this is a simple way for you guys to understand it. So then because the IMU is 0, our error is equal to target minus the current, and the current is 0, so it's just equal to target. While the magnitude of our error is greater than 10 degrees, i.e. we're not within 10 degrees of the final desired angle, we keep repeating this, and what we do is we set our error equal to our target minus our current heading, and then we set the powers of our two motors. So again, we have 1 divided by 90 so that it starts slowing down at 90 degrees. And then this one starts slowing down at negative 90 degrees. The reason there's a negative here is because if they were both positive, the robot would go forward. One goes negative, so one forward, one negative, and then the robot spins. And then at the end, we set the powers to 0 so that the robot does not keep moving at the end. So that's something we should actually add to this one as well. Okay, great. So now that we have gotten both of those done, we can come into here to wait for start. This just waits till the program starts, and then we can add in our two methods. So let's add a drive distance of, we'll say, 50 centimeters. Then we will, what's the method called? Turn degrees, we'll turn 90 degrees. And then we can just repeat that in a loop. So this is just a for loop, so we'll repeat 4 times. and this just makes a square. Very, very simple square. We can see if that works properly or not on a drivetrain later. Right, now let's go back to the presentation. Sorry about that. All right, that's the end of our presentation. This week assignment is posted in Discord. It's the same as the last week's assignment, and you just need to send in a screenshot. We create a program in Android Studio and add a motor and servo to it. If you have any questions about that specifically, post it in the Discord. Okay, do we have any questions? Other than that, I think everything is done. Okay. Well, thank you guys for showing up. Again, if you have any more questions, post them in the Discord. All right. Bye, everybody.